No recording progress or something? Oh, it's good. Okay, everybody. Thank you for being here, and welcome to this analysis junior seminar. Today's speaker will be Davide Donati from SISSA. He will tell us about a matrix valued measure associated to functions of generalized bounded deformation. Please, Davide, go.
Okay, thank you, Marco, for the introduction. So, as you see, I'm going to talk about functions of generalized bounded deformation and about the work that I've carried out in collaboration with Gianni Dal Maso. And so, in order to be able to present to you this result, I would like to briefly mention what functions of bounded deformation are. Okay, so the definition of functions of bounded deformation is very close in spirit to that of BV functions, for those of you who have seen it. Which are defined as L1 functions such that the distributional derivative is not, are not, as in the case of Sobolev functions, gradients, but just bounded random measures. In this case, what BD functions are going to be L1 vector fields, so the image of the dimension of the image matches that of the domain, such that not the distributional derivative is a measure, but an operator associated to it, it's a distributional measure. We are going to require that E of U, which is the distributional symmetric gradient, which is defined as U plus the transpose of the U, divided by 2 is a bounded random measure. They were introduced at the end of the 70s by Souquet and independently by Matthias, Strang, and Christiansen for certain problems related with elastoplasticity, so with, let's say, materials. And it arises naturally when one looks at energy of these forms. So we have F, which is a function that has linear growth at infinity. And here we have calligraphic E of U, which is the symmetric part of the gradient, for instance, for a W11 function. And in these cases, when one looks at sequences UN which have bounded energy, such that the supremum over n of F of calligraphic E of UN is bounded, then we may extract a subsequence which is inconvergent in these cases, if one has Dirichlet boundary conditions or the control of, for instance, also under one norm. But the limit is not going to be in W11, it's going to be in BD. Essentially, as happens for BV functions, where if you have here the gradient instead of the calligraphic keys, we obtain a sequence, a limit which is in BV and not in W11. And also what you may note is that, unfortunately, the space BD is strictly larger than BV. As you may produce examples of functions which are bounded deformation but not bounded variation by using this famous known inequality by Ornstein, which tells you that there is no constant that allows you to control the gradient of a function, of every function, every smooth function by means of the integral of its symmetric part of the gradient. So if one wants to study BD functions, one cannot really rely only on the theory of BD functions, but has to work with the properties of BD functions concretely. And for this reason, in 1997, there was this very well-known paper by D'Ambrosio, Koch, and Dal Maso, where they studied the fine properties of functions of bounded deformation. So their starting point is similar to the starting point of the theory for BD function. You look at the measure E of U, and you decompose it as the sum of 3 contributions. This first part is the absolutely continuous part, which is the part of this measure E of U, which is absolutely continuous with respect to the Lebesgue measure. And then you have these two pieces which are singular with respect to the Lebesgue measure and are the jump part and the Cantor part. This one essentially weights the jump discontinuities of our function U. This one instead something in between the absolutely continuous realm and the jump realm. And I mean, this decomposition is immediate, it's just a definition, basically. But then what they also do in the work is they characterize what each one of these pieces is. For the absolutely continuous part, they compute what the Radon-Nikodym derivative of this function with respect to Lebesgue measure is, and it's this approximate symmetric gradient, which, I mean, essentially is telling you in a measured theoretical sense that this is the classic symmetric part of the gradient. Then the last term, the jump part, is basically the Hausdorff measure of dimension d-1 concentrated on the jump set, or the function U, which is a d-1 dimensional rectifiable set. So imagine a surface such that every time I pick a point here, x, if I get close to x from one side, I see one value of plus. If I get to the other side, I say one value minus. These two values are different. So my function is essentially jumping. And since they also prove that this set is rectifiable, you can also define a unit normal for this set. And then you basically, I mean, for this part, you have basically the Hausdorff measure restricted to this set. And as an integrand, instead have this bracket u, which is u plus minus u minus. And then since this has to be a vector, this is telling you in which direction you're jumping. And this is the symmetric product with respect, I mean, of u with normal, which is basically the symmetric part of the tensor product between u and its unit normal. And finally, for this last piece, I mean, you cannot deduce, let's say, an explicit expression, but for this Cantor part, you will know that it's, on the one hand, singular with respect to the peg measure, but on the other hand, it will vanish, will not give any measure to all those sets which are essentially d-1 dimensional. Good. Once one has this decomposition, you can start doing a bit of calculus of variations. And for instance, you may study integral functionals which are, let's say, tailored to this decomposition. So here, for instance, we have a bulk term depending on the absolutely continuous part, a surface term depending on the jump part, and then we have a term depending on the Cantor part. Here, this denotes the Radon-Nikodym derivative of the measure ECU with respect to its total variation. So it's going to be a unit vector. I mean, in general, for lower semi-continuity reasons, you're not going to consider any function h. Normally, there's a relation between h and f, as we're going to see later. But this is, for instance, the prototype function that you want to study in this space. And let's say the model functional that was the most studied in this setting was the one that you obtain if you take here f equal to the squared norm of Hilbert-Schatten norm, for instance. Here you take 1, and here you take h equal to 0. In this case, you recover Griffith functional, which is the BD analog of the Mumford-Shah functional, and is well defined. You normally study it on SBD, which is the subspace of BD functions for which the middle term of the previous decomposition is not there. And this function is very important, and it brings the name of Griffith because it comes is really relevant when one studies a fracture of brittle materials. Griffith was an engineer who published this seminal paper in 1912, I think, 21 maybe, where he was studying in which he shows that materials that break generally satisfy a certain energy. I mean, there is a certain competition between energies that you have to check. Your material will want either to bend and deform elastically or break, depending on what's the more convenient thing for it at that moment. And then this Francfort and Marigot, at the end of the 90s, they formulated this idea rigorously in a mathematical framework, and let's say that the key piece of this theory is minimizing this functional. So, but one would want to minimize this functional with, for instance, Dirichlet boundary conditions, and that's the first starting point for this theory. But one soon realizes that these Dirichlet boundary conditions are not enough to minimize in this space, because the problem is that Griffith functional plus Dirichlet boundary condition does not guarantee compactness of minimizing sequences, unless one, for instance, has a bound which is rather unnatural on the L infinity norm of the minimizing sequence. It's the same problem that happens, for instance, in SBV. And the classic example is the following one. Pick the unit disk and pick as a Dirichlet boundary condition, for instance, u equal to 1. Then your sequence is going to be, can be, for instance, be of the form, at the step 1, the characteristic of the circle. Then you cut a smaller circle, but you make the jump very high, but you do it in such a way that you're not taking the circle too big. And then you build a tower like this, in such a way that the sum of the jumps is going to be plus infinity, and that's the energy that Griffith functional assigns to the no, that's not the energy that Griffith. The energy that Griffith functional assigns to this energy to this function is to this sequence of functions is just the sum of the perimeters of the circles. But then if you make the jump very high, you can make the perimeter be finite at the same time. The integral of the jumps be plus infinity. And I mean, this example also works for, let's say, Mumford-Shah function, so for the DV setting. And to deal with this problem in the DV setting, Ambrosio and De Giorgi, okay, these are not the slides. There's a mistake. This is a paper from 1988, not 1990, and it's not on ARMA. But, I modified it before. I think I didn't download it. Well, in any case, the way they dealt with this problem was the following. So I know that I would want to expand my space in order to include the limits of sequences as the one that I presented before. So I want these towers to have a limit in my larger space. And I know that I have a limit as long as in SBD, as long as I truncate my functions in such a way that they are n infinity. So their space is going to be the space of functions such that every time I compose it to the left with a smooth function, with a C1 function with compact support, I obtain an SBV function. In this case, the functions that will obtain will be an SBV and have L infinity norm bounded by the maximum of psi. So you can select, for instance, in this space, a sequence of truncation functions. At any level, you use the compactness theorem for SBV functions. And then as long as you have a condition that tells you that your functions are not escaping an infinity, you will recover compactness. The only thing that one should check is that the energy of this function here is going to be bounded by means of the energy of the original function. And this is simply a computation. If I take the gradient, for instance, for a smooth function of this composition, I will obtain something which is the derivative of psi composed with the gradient of u, which can be bounded in norm, but in terms of the Lipschitz constant, it can be set to 1, for instance, time the modulus of the gradient of u. But the problem is that if I do the same, I try to take the same approach with calligraphic key, I obtain something which is not controlled by means of the original calligraphic key of u. So this approach is too naive to deal with the symmetric gradient operator. And this is where a work of Dal Maso comes into play. He realized that truncations were fundamental to deal with this problem, but one had to be more subtle about this. So introduce the space of GBD functions, so functions of generalized bounded deformation, as the space of those measurable functions from omega into RD, for which every time I pick a direction sign in unit sphere, and anytime I pick a truncation function that here is not from RD into RD, it's from R into R, because I'm going to truncate components of this function. And I suppose that I have a control on the derivative of these functions and that their image is constrained in a box. Then if I look at this distribution here, it's actually a measure. So what is this distribution? I'm looking at the component in direction psi of u. This is a measurable function. So I cannot take the distributional derivative. So I need to compose it to the left with a truncation function. Now I have a L infinity function from omega into -1 alpha and alpha. I can take a derivative. Now this is a distribution. I suppose that the one in direction psi is a measure. And then I also suppose, here is where the bounded part comes from. I suppose that there is a uniform bound independent on psi and tau by means of a universal measure lambda, which is a positive measure. And how does this relate with bounded deformation? Well, suppose, for instance, that u is a function of bounded variation. Then we have a chain rule for these functions. And when I develop this expression, what I'm going to recover is on the absolutely continuous part and the Cantor part, let's say, essentially the symmetric gradient. I mean, modulus that you factor here, I have the derivative of tau. But for instance, if my function is something like this, it's the identity, and then it becomes constant. tau prime is going to be always equal to 1 and then 0. And so here, basically, I can think that, I mean, just opposing a lot of functions like this, I can think of here having exactly E of u and EC of u. But on the jump, something funny happens. Because now, because of the chain rule, here I'm going to have something which is not the jump of u, but is the jump of the truncation of u. So here I have an object which is at most 1. So I cannot expect this object, or the total variation of this object, to give me a bound on the, let's say, on the integral of the modulus of the jumps. But I will have a bound on the integral of the modulus of the jumps when the jumps are small. But when they are larger than 1, here this object is going to make me pay only 1. So a key role, which is hidden in this definition, should be played by the set of points in the jump set where my jump is large. And to see more clearly a definition that decodes this property, we want to talk briefly about slicing of BD functions, because it is the key point behind the second equivalent definition that Dal Maso gave of GBD function. So, okay, one-dimensional slicing is a very useful tool when one deals with the calculus variation, with problems in the calculus variation, because it allows you to reduce a problem which is d-dimensional to problems which are one-dimensional and usually easier to treat. And it relies on the general understanding that having regularity properties for your function, for instance, being BD as a function of deep variables, carries out, yields some regularity properties for the one-dimensional sections. Just to set some notation, given xi, which is going to be a vector in the unit sphere, pi xi is the plane, the hyperplane orthogonal to xi, and passing through the origin. And any line parallel to xi, or direction psi, can be parameterized by choosing a point y on this plane, and then summing to it t times over t is a real parameter, the vector xi. So what I require, what Ambrosio Coscia and Dal Maso strongly used also in the paper, was that if I take the restriction of my function to one of these lines, and then I take the projection of this function in direction psi, so here you can imagine of having a function of one variable that moves along this line. To every point it associates a vector. If I project this vector on this line, what I obtain is this function u psi y, and this is going to be for almost every point in the plane a function which is PV, so that I can take derivatives of. And the very key, the key idea in all this machinery is that I can reconstruct the full symmetric gradient by averaging the derivatives of these functions. So if I pick a Borel set B and I want to know what E of u of B is going to be, at least when evaluated on psi, scalar psi, or at least when I evaluate the quadratic form associated to this matrix on the vector psi, is going to be given by the integral over the points y varying in this plane of the derivatives of these one-dimensional functions. And so I should expect, in the BD case, this essentially tells me that I can control EU of B psi xi by means of the total variation of this, the integral of total variation of this one-dimensional section. Right? And this is a quadratic form, so if I want to control then the components of the entries of this matrix, I can use it's a symmetric matrix, so I can use the polarization identities. So these, knowing this for instance, for a basis of vectors, for n times n plus 1 over 2 vectors, will give a bound of the full total variation of u of u. But so starting from this idea, one could try to give a definition of GBD that passes through sections. The only thing is that here we cannot have the full derivative, right? Because as I was mentioning before, small jumps should be controlled, but large jumps should be controlled in a weaker sense. And the idea is that the object that we want to control is, again, the derivative of the slices on on that part of the Borel set where my function is the one-dimensional sections is jumping not too much. Here, J1 of U set Y is the set of points in the jump set of the slice U psi Y, where the jump is larger than 1. And then I should penalize instead the number of the points at which this one-dimensional section jumps a lot. This is what I should control. And this is the second definition that Dal Maso gave of GBD. For me, a GBD function is also a function such that almost every time I pick a point in the plane, I take the slice, I obtain a BV log function, and the average of the total variation of these derivatives when the jumps are small are controlled, and also the number of jumps that they make is controlled. So we have this very weak space in principle, and we would like to know that we can. We introduced it to study brief-fit functional, right? We would like to know that we can study brief-fit functional. So we have to be able to give a sense to the evaluation of brief-fit functional on GBD functions. Thank God, thankfully, Dal Maso was able to prove in the original paper that even though you cannot consider E of U, because our function is just measurable, so you cannot take distributional derivatives. Even though it is just measurable, using this definition by slicing, we can prove that it meets an approximate symmetric gradient, that the jump set is rectifiable, and the jump satisfy many good properties. And for this reason, you can also define a GSBD space. You can add the S here, and you can study this functional here. And then, thankfully, after a lot of work, Friedrich and Solombrino in the planar case, and then Chambolle and Crismali in the general case, were able to prove that this functional can be minimized under the Dirichlet boundary conditions in the GSBD space, and also adding some, more reasonable lower order terms rather than just the L-infinity norm. Good. So this settles the problem for the Griffith case, let's say. But what if we are interested in functionals that have all the three pieces? So I want to encode now the Cantor part as well, because, for instance, I want to study functionals that here don't have a square, but they have something which is linear at infinity. Here, for instance, I want to encode something which is linear in the origin, which is usually the case when one wants to study not brittle models for fractional mechanics, but cohesive models. So models in which the two lips of the crack may interact. For instance, in this setting, what I'm assuming is that they are going to interact when the smalls are jumped, but after a certain time, the sleeps are going to be too far away to interact between each other, and so they, I'm paying something which is proportional to the crack, but that crack might be at infinity, might be as far away as I want. The two lips are not interacting, so they shouldn't pay for the size of the clamp. Well, in these cases, when one assumes that G has this linear behavior at the origin, then by lower semi-continuity reason, I'm forced here to put a contribution due to the Cantor part, because small jumps might become denser and denser, and they become they may form a diffuse structure. And also, for lower semi-continuity reasons, I should put here not any function h, but I should put the recession function of f, which is basically telling me the slope at which f is approaching. F has linear growth, so in any direction it will have, let's say, a slope. And this f infinity is telling me exactly that. Well, the problem is that this is the natural setting for this function. For this problem, this is the natural function to study. But the same example that I showed you before, the tower thing, shows that there is no compactness in BT for these functionals. And so one would want to define them on GBD, but then the problem becomes, what do I make of this measure? Because in the BD setting, the way I defined it was, I was picking the singular part of the measure U, and then I was restricting it to the complement of the jump set. But here I don't have a measure of which I want to take the singular part, and I have nothing to restrict. And I don't even have a distributional derivative. So I want to stress that it's a priori non-trivial, the definition of this measure. And this is what we tried to deal with together with Gianni last year. So it was finding a canonical way, given a GBD function, to associate with a Cantor measure, a Cantor part. And I mean, in order to state the result that we managed to prove, I would like to introduce a bit of notation. I mean, tau r is a specific truncation function. It's a truncation function of that form. But just I'm assuming that it's not restricted to have values in -1/2, 1/2. I'm taking larger and larger intervals in which is equal to the identity, and then the intervals are parameterized by this R. And then this is going to be one of the main characters of the statement of the following theorem. This is basically the object that I had in the definition of GBD. The only difference is that this is a measure with sign. Here I don't have the total variation anymore. This is can be also negative. Since I want to consider it for vectors which are non-unitary, here I have to put a factor to make it homogeneous with the right scaling. And then, since I don't want problems and I don't want to really deal with this set of ill-behaved jumps, I'm not taking away the jumps, the large jumps of the section. I'm taking away the large jumps, all the large jumps. Okay, the main theorem that we managed to prove is the following. So given a function u in GBD, we can always construct a measure mu of u, bounded with values in the space of symmetric matrices, such that every time you give me a direction in the unit sphere and a Borel set, I can compute the value of the quadratic form associated to mu u in B by simply looking at that integral defined by slicing that I had in the previous slide, or by looking at the derivative in direction psi of this truncation of the component along psi of u with the truncation function parameterized by R. And I have to do it away from the set of ill-behaved jumps. But then taking the limit as R goes to plus infinity of this quantity, I recover the value of this matrix valid measure evaluated on psi. So it is a way to construct a matrix valid measure associated to the only derivatives that you can define for these functions. So derivatives of the truncations of the components. And also we characterize what's the norm, the operatorial norm of this matrix. But okay, since this should be a generalization, let's say, of the EU when I mean, it should coincide with EU when U is a bounded BD function. I mean, this is easy to see that happens. It's just because by the identity that I wrote before, no? This one. If I take away the set of bad jumps and I evaluate this, what I obtain is for a unit vector at least is exactly this object here, which then by our theorem coincides with this with this one, and so the two measures should coincide. So it's really a generalization of the measure EU, at least away from the jump set J1 of U. Then, I mean, once we have this measure, we did exactly what Ambrosio, Coscia, and Dal Maso did in the original work. We split it into 3 pieces, and then we tried to characterize it, what those were. And I mean, everything that happens is what one would expect. So the absolutely continuous part coincides with the one that Dal Maso constructed in his original paper. The jump part coincides away from the set of large jumps, what Dal Maso constructed. And then we also characterize by means of slicing the Cantor term, which yields as a corollary that this Cantor measure does what a Cantor measure should do. In sense of it doesn't weigh sets which are essentially d-1 dimensional. And finally, the one last application of this result that we constructed is the following, which I find quite nice. So in the originally SBD was introduced not by the way I defined it before. So as the set of BD functions where the Cantor part is null. But it was defined by slicing, by asking that basically for almost every slice, once you fix a direction, you're going to see SBD functions and not BV functions. So your one-dimensional section shouldn't have a Cantor part. And since Dal Maso in his original paper didn't have any Cantor method for the GBD functions, well, he defined it by slicing as well. So GSBD is the space of GBD function whose slices are SBD. Now we are able to complete the picture, and GSBD functions are is the space of GBD function whose Cantor part is 0. Which, I mean, also has some nice applications, because if this is asking you to check something for every vector psi in the unit sphere, this allows you to pick just a finite number of them. So if you're able to check that in a finite number of directions you don't have, your slices don't have Cantor part, then you're good to go. I would like to conclude this seminar by giving, let's say, a sketch of the proof to make you understand where the complication comes from. So, okay, the main theorem that we have to prove is the first of the two equalities in the statement of the result that I presented. So here I think I wrote the things in the converse order and I changed in the slides that I forgot to download. But yeah, for every direction, for every direction and every Borel set, we should construct. For every Borel set, we should construct a measure mu u, a matrix mu u of B, such that for every vector psi, we have this identity. Okay. Once you know that for every Borel set you can construct such a measure, such a matrix, it's easy to see that this defines a measure as a map from the Borel sets into RD times DC. So the really complicated part is constructing this matrix mu u of B. But well, here on the left we would have a quadratic map, and what we would like to then show is that this is a quadratic function. If it is a quadratic function, then there should exist a matrix that does this job. So what we want to prove is that these three properties are satisfied. So our map sigma psi of u as a function of psi for a Borel set B fixed should be lower bounded. This is easy to check that it holds. Should be two homogeneous. This is also easy to check because it's basically a change of variables on the slices. And then there is the complicated part. Right? One for every couple of vector of psi and eta, you should check that this function of psi satisfies the parallelogram identity. You see, this is the complicated part, right? Because what you have this sigma psi is an integral of restriction of your functions to certain lines, and it's an integral over a plane which depends on psi. Now you will pick two random vectors, so you will pick another plane and you will pick another direction, and you should be able somehow to compare these two quantities, and also to compare them with their sum and with their difference. So it's, I mean, it's to me it was really quite surprising that we could do it in the end. But the idea is the following. Right? So the first two, as I said, they're basically for granted, right? You should check this one. But this one, for the first observation, is that it is a two-dimensional matter, because the parallelogram identity is a property of the plane generated by the two vectors psi and eta. So this needs to be made rigorous by means of a Fubini argument, but the real case is the two-dimensional one. And also, it is enough to study the case where the Borel set for which we want to construct a measure is a parallelogram, because for general Borel sets, we can cover the open set by parallelograms, and for Borel sets we can approximate from outside with open sets. So the real case is when we have B is a parallelogram whose sides are parallel to psi and eta, which we may assume to be not parallel. Otherwise, the parallelogram identity is too homogeneous once again. Well, the key observation is we can use the fundamental theorem of calculus. So if I take the one-dimensional section, for instance, related to psi, with base point the projection of this vector on this vertical plane, then if I evaluate this measure on this segment here, V1, V0, this derivative is simply the difference of the function of the endpoints times psi, because there was a times psi in definition of the section. So I have a way of transforming the integrants that I have in my sigma xi into differences of values. So this, I mean, of course, I can do it for all the other directions and for the diagonals. And using this fact, I may hope to prove a sort of discrete parallelogram identity. So starting, I want to check that the psi plus zeta, psi minus zeta, they relate with 2 times psi, 2 times zeta. So here I start from this, I use the fundamental theorem of calculus, I obtain this, the sum of these two differences. Then I rearrange the terms, and what I obtain are sums of two different contributions, which are of terms parallel with psi, and two terms which are parallel to eta. And then I can reuse the fundamental theorem of calculus once again, and I obtain what I want. So two contributions related to psi, two contributions related to eta. Just that they are shifted by one side, no? I mean, then the idea would be, okay, I start from this sigma psi, sigma z of u for any z. Using, okay, Dal Maso would say using a theorem of Hahn from a German paper from 1912, you can prove that. But unfortunately, I cannot read German as he does. So I had to rely on a modified version of a lemma that he proved in a beautiful paper in collaboration with Frank Foer and two others, and that we had to pseudo-modify. But you can look at this integral here, and even though this is just a measurable function, treat it as if it was Riemann integrable, so approximated by means of Riemann sums. I mean, you have to choose carefully which base points you're choosing, and you should fix a representative for this function. But once you fix a representative, and once you take the correct base points, then you can do this machinery. And then, for instance, if I do this with psi, let's say, equal with z equal psi, okay, my B is a parallelogram. So when I take section, this is going to be a segment. I can divide it into, so first I approximate with lots of lines on this place. Then on a single line, I divide this segment in many more small intervals. And then so that I can decompose this sum as a sum over two indices of these derivatives on small intervals. But again, I have to be careful, because I also have to take away the part of the jump set J1 of u that I don't like. This is very important. And okay, how I'm going to choose? There is a specific way in which I'm going to choose this YY. I'm going to choose them as projections of the vertices of a grid made of parallelograms that I will move around a bit in order to select correctly these points YY. Because what I basically want to do is I want to approximate this object with sums, where here I have the sides of the small parallelograms, so that I can use the discrete identity that I proved before. And now, if the jump set, the part of the jump set where the jumps are larger is small, so or non-existent, let's say, small is not enough, it's non-existent, then I'm done, because here I don't have to take away anything. So I can take these two integrals, discretize them, and then here I just have the derivative of u on intervals. I don't have to take points, I don't have to take anything. So I can use the discrete identity that I had before, rearrange the terms, and I would obtain two contributions related to psi, two contributions related to eta. Then I send k to infinity once again, and I recover this nice identity. The problem is that this is really, really restrictive. The moment that you know this, you know already that your function is BD. And I mean, for BD function, the fact that this map is quadratic is obvious. So, I mean, one should expect that this is something that never happens. I mean, and indeed, the complicated part of the proof of this theorem is making sure that this argument can be carried out even though you have a positive measured set of large jumps. So we will define what for us a bad indices in the grid will be. Will be basically the index related to a vertex, such that if I construct the small parallelogram of the grid, at least one of the sides or the diagonal is going to meet J1 of U. Because this is the part where we are going to have to remove some points from our discrete sums, and we will not be able to use the fundamental theorem of calculus. And then the really complicated part of the proof, which takes a long time, is proving that if you restrict your sums to this set of bad indices, this may be, I mean, choosing correctly the grid. This is the fundamental point. It's not like it always happens. But by choosing correctly the grid from which you're projecting these points for the discretization, then this can be sent to zero. Yeah, once you're done this, you can repeat the machinery that I had in these previous slides, and everything works fine. And this concludes my talk. Thank you.
Thank you, Davide, for your talk. Are there any questions? I do have a question.
Yeah.
It's perhaps a very dumb one, but at some point you were talking about approximate distributional gradient of ED or GBD function, more or less in the beginning. When you define that, do you use similar machinery with the truncation business for function to stabilize somehow? When you have
you mean for GSBD functions like here? Here.
Point.
Or do you mean here in the?
My bad. Just this one.
Yeah.
I was just thinking. In general, you have a way. I don't even know if it makes sense somehow, but basically, when you define the counterpart, if I understood correctly, you just truncate and show that more or less when the function is bounded, it stabilizes so that you get a random measure. I don't know. I was thinking because this truncation business reminded me of something I saw in a literature once. And you don't know if the rationale behind it was like this.
I think I understood correctly the question.
Basically, if you have the you just truncate the function. Once you send the truncation to infinity, you expect at some point, sooner or later, every point to stabilize the value.
Yeah.
So this is what tells you that, if I understood correctly, the random measure stabilized, converted to something, basically, for instance.
The problem is that truncations here are not the correct thing to do in the BD setting.
Okay.
Just because if you take a decomposition to the left with a smooth function,
you don't control it.
No, it's not only you don't control it, but your BD function composed on the left with a smooth function might not be BD.
Yeah.
So it's just an operation that's forbidden because you immediately exit out of the space unless the function you compose with is like affine.
Oh, and so that's why you do this slicing.
You should still, let's say truncate, but you cannot truncate the full function. Otherwise, you get something which involves all of the derivatives of the function u, if u is smooth, and so you cannot expect to.
Right. Okay. Now I see.
It's you immediately go out of the space.
Thank you very much. So if there are no more questions, let's thank Davide once again.